Take a guess. Okay, so inductive means that there is, well, let me give an example of inductive reasoning for this kind of situation. So inductive reasoning would be, I have 5 friends and they took it to 5 mechanics and they all said it was going to be done in a week and it was 10 days. Therefore, it looks like if you go to a mechanic, it's going to take, and they say a week, it's really going to take 10 days. Okay. In this case, the first sentence says, if the mechanic says, so the first statement is actually a statement. This is like a general observation. And then the second part says, I'm going to go to a particular mechanic. So it's actually deductive reasoning in that case. And yes, got the right answer. Good. That would be the difference. Do you see that? Yeah. Okay. It has rained every day for the past 6 days. It is raining today, so it's the last 6 days. It's raining today. Therefore, I'm going to say that it's going to rain tomorrow. Okay. How many? Let's do a vote here. So, how many people think it's deductive reasoning? How many people think it's inductive reasoning? Very good. Okay. Because he's observing. He's saying it's rained for 7 days, so my observation is it's going to rain tomorrow. He must live in England or something because it always rains there. Okay. If you build it, they will come. So then you build it, therefore they will come. So let's do another vote here. How many people say inductive reasoning? How many people say deductive reasoning? So we're about split on that one. Okay. Yeah, this one's a little difficult. I mean, it's trying to give an example of what the other option would be. So I'm going to give you the other example that's not this one. That's the opposite kind of reasoning. The Egyptians came and let's see. No, that's not it. Let's think about that. Maybe I can't come up with a good example. Anyway, the answer is, well, let's look at it. The first statement is actually a general statement. If you build it, they will come. Okay, so that's the general statement. The following one is, so you build it. That's what's happening. Now you're going to build it. So the first statement's about you as in a global you, a royal you, or something like that. Maybe it should be if they build. You is in a plural you. Okay. Whereas the second you is a singular you. Maybe that would be easier. So it actually is deductive reasoning because the first sentence is the general statement and the second part is a specific example. That was a little hard. It is the fact that every student who ever attended Delgado University was accepted into graduate school. Because I am attending Delgado, I can expect to be accepted into graduate school too. Okay, here we go. Deductive reasoning. Inductive reasoning. Okay. Yeah, in this case, because they're talking about every student, so it is an example of where you are looking at past experience. You're looking at examples. It's like the rain example, which everybody got right. So in that case, we're going from experiments, which are everybody else prior to this, going to a general conclusion, which, well, actually, that's a good question because it's saying I am accepting, so maybe not. Let's think about that because I almost convinced myself that you were right. So I think if it said it is a fact or it is observed, maybe that would have been a difference. If it has been observed that every student who ever attended Delgado University was accepted into graduate school. Therefore, any additional student who attends Delgado will get into graduate school. Whereas this case, the fact that they said it's a fact, so that's a general conclusion. A little tricky. See if the book agrees with me there. So I said it was deductive reasoning. Oh, actually, I said it was inductive reasoning. Oh, I was wrong. Interesting. Faculty student. Okay. So actually, you can kind of argue either way on that one. Maybe I'm just wrong. Yeah, maybe the word fact doesn't make any difference. Okay, interesting. Okay. Okay, so what you'll do is I'll give you an assignment here in a second, which will give you some more chances to work on that. Okay, the next thing is just some numerical examples of, these are examples of inductive reasoning. So we're going to have a sequence of numbers, which is like an experiment. And the first couple are easy. So look at those numbers. I'll see if anybody wants to tell me what the next one is. It's not hard, so don't think I'm trying to trick you or anything like that. You should be able to get that. What's that? Exactly, 21. Okay, so you notice that each number in the sequence is 3 greater than that. So, and does anybody know what kind of sequence that is? We don't talk about it until later. I don't know, maybe we do. Can't remember whether we do or not. Oh yeah, we do talk about it. Okay. We actually talk about sequences in the next section, but these sequences are just examples of deductive reasoning. So it's actually called an arithmetic sequence, which we'll talk about in the next section. But right now we're in first section. Okay, so the answer is 21. You might have to get your calculator out for that one. Or you can do it by hand. Didn't bring my calculator, so I'll have to. So what's the law? 4? I heard 4. Yeah, it's the first number and each subsequent number multiplied by 4. So 3 times 4 is 12. 4 times 12 is 48. 4 times 48 is 192. 768 times 4 is, I'm trying to think if I could figure an easy way of doing that in my head, which I don't think I can, so let's just do it quickly. I get 2972. Okay. We'll move quickly so you can't prove me wrong. No, just kidding. Okay. So what's the next fraction?
11/13.
What's that? 11/13. Yep. Yep. So just the numerator and the denominator are each increased by 2. Somebody from that table, second table. This one right here. Yep. I'm not sure if I know what, yeah. Can you do that in your head? Do you know what the rule is? Anybody else? Cubing it, yeah. So it's 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and 6 cubed. And 6 cubed is 36 times 6. I don't know what 6 cubed is. So it's 36 times 6, which is 696, I guess. No, 236 plus, no, 260. So 6 cubed is 260. I'll give you a hint. It's either a 3 or 5. You have a 50% chance of getting it right. So how many people vote for 5? How many people vote for 3? Okay, so yeah, it's 5, because you see you've got 1 5, then 2 5s, and 3 5s, 4 5s, with a 3 interspersed in it. So then you'll have 5 5s. So we need 1 more 5 right there. And then we have these new set of problems, which are basically there's 4 examples, and you have to kind of come down and do the next example. So whatever the next one is there. So yeah. Obviously, the first part is that. What's the second part? 15. And the third part is 50,505. So that's kind of interesting that it would happen that way. You know, always, if you're a number person, you're like, oh, that's cool. Okay, so what's the next number? 15. Okay. And then this number is here. 15. Yep. And this number is 6, and the bottom is 2. Yeah. So 3, 6, 9, 12, 15, 2, 3, 4, 5, 6. So okay, so let's write all this stuff out. So obviously all the stuff, I left a space out here. I've got a plus. Sorry, I left something out there. 5. So there's got to be another term here. So this all goes on the left-hand side. So it looks like 5 is the thing in the front. Since we don't have our calculators, what's the next number going to be in terms of the previous number? So this number is how many times this number? 36 is how many times 6? 6, right? 6 from this previous problem earlier, you might have forgotten it, but the next one was 216. I remembered that. So that's 216. So 6 times 36 is 216. 6 times, actually, yeah, we go to 315, not 330. I remember that. 6 times that is 1296. So this is going to be 6 times 1296, whatever that is. And then the same right here. So this number, these two numbers are the same. So this is going to be 6 times, pardon me? Oh, what, 6 times 1296 is, I'm not sure what it is. Okay. The last thing, which we may not completely finish, so this is an interesting one. So does anybody have any idea how you would do this problem without just adding up 800 numbers? This is a famous experiment or a famous story, whether it's true or not. There was a mathematician. If you take engineering or math, the name. Let me see if you guys, anybody has heard of this guy. Has anybody ever heard of Gauss before? So he was a German. I think he was German. And you'll notice if you ever go on the internet, some people have attempted to put on a IQ scale, you know, who the most intelligent people in history were, which is hard to do because they were at different times and they discovered different things. So, you know, somebody like Newton or Albert Einstein or, you know, all the top people you might think of. So Gauss is one of those guys. He did things that nobody else. Another guy whose name was Euler, E-U-L-E-R. I think this is Gauss, not Euler. Let me just check to make sure I've got the right guy. Yeah, it's Gauss. He's so famous that the force the force of attraction between a magnetic attraction, you know, like magnets. The unit for magnetic attraction is a Gauss. Little trivia fact there from physics. And so I think he got in trouble or something like that. And he wanted the teacher wanted to keep him busy, or or they said to the class, you know, he wanted to go over and read some book or whatever. So he gave his class, he says, okay, class, I want you to add the numbers from 1 to 100 up. And so all the other kids said 1 plus 2 is 3, 3 plus 3 is 6. And Gauss went over there and like a minute took his answer to the teacher. I'm done. And he thought, how the heck did he do that? So here's the secret. What he did was, if I put 799 here, you'll notice 1 plus 800. If I rearrange these terms, I'll get, I can group them. So I start from the top and the bottom and I go down. So this is 801. This is 801. This is 801. And so, and how many pairs are you going to get? Well, when you have an even number, you're going to get half of 800. Okay, so you get 400 of these pairs. So they're going to be 400 pairs of 801. So that's 400 of 800 of the sum of 801. So you take 801 times 400. Which is 0. So you got 2 zeros here, so we put 2 zeros here, and then you do 4 times 1 is 4, 0 times 4 is 0, 8 times 4 is 32. If I did the math right, I did that 4, 0, 32. And so the answer is 320,400. And that's the answer. Okay. So that's just an example of somebody using some reasoning instead of just doing it the brute force method, which would be adding all the numbers. I don't know how long it would take to add those numbers together. For an odd number, it's you have slightly different, but you can kind of have you have a middle number that doesn't get matched up, and then it takes a little more time. Okay, so there's those are the in-class problems. So. Which probably not the ones I just did. There's a homework assignment. Let me delete that page. So they're basically just what we did in class, looking at some statements, determine whether they're inductive or deductive reasoning, looking at patterns, and the last two are using Gauss's, I don't know if it's called Gauss's theorem or what's it called? It's probably just called Gauss's method or something like that. Okay, so that's it for today, and we will see you Thursday, either here or online. Did I forget anything? Is there anything I forgot to tell you that you need to know? So don't remember, over in the libraries, the memory stick to get your homework assignment copies. If you're going to try to attend online, you might want to just try connecting with that before class, like tomorrow, so that if you have problems, you don't find out at the last minute that it's not working. A little side thing, so everybody's got their Cokes, right? Water and Coke, okay. I don't like water. I mean, I'll drink water when I'm really thirsty, but I do like flavor. So if you ever come to my office, every once in a while you'll see about 30 Coke Zero cans on my shelf. And it's not that I'm collecting them, I'm recycling them. But my wife doesn't like it because she thinks the artificial sweeteners are worse than the sugar, which I don't know. I only have 1 can a day, so it's not, I don't have an addiction, I don't think. Okay, so section 2 is similar to what we did at the end of section 1, but we're giving it a name. We're going to give some of these sequences names. So a number sequence, and these are all definitions in your book, and I'm not going to ask you to do definitions, so if you just want to pay attention, that's fine. you'll need to identify whether something's an arithmetic sequence or a geometric sequence or neither one of them. So a sequence is just a listing of numbers, and each number in the list is called a term, or yep, that's what it says, term of the sequence. There are two main types of sequences that we'll look at: arithmetic sequence, which we saw yesterday, and what basically you have a first number, and then the second term is some fixed amount greater. So you add or subtract. You know, you could be, well, it says of adding. I don't see why you couldn't have subtracting, but I guess in general you do have them where you add them the same number. And we'll look at some examples here in a second. And geometric sequence is where you have the first number and then you multiply each subsequent number by a fixed given number, which is called the common ratio. You've had this long ago in probably 5 years ago, so it's nothing new for you. But the reason we're talking about it in this college level class here is because these are examples of inductive reasoning. We're looking for a pattern. We're coming up with a rule, whether it's a stated rule or whether it's a just, I think the next one is this because I've noticed this pattern. So that's why we're talking about it. So here's two examples. The first one is an arithmetic sequence, and I don't think I'm not going to ask anybody because I think everybody knows what they can see what's happening here. You look at each number in sequence, and you see that there's a difference of 5. And so what I'm going to ask you on a test is, given this sequence, you're going to tell me what kind of sequence it is and what the next number would be. So the next number would be 28, okay, because you had 5 to 23 and you get 28. Okay, so that's, and this would be the common difference, not this, 5, let's just write it down, 5 is the common difference. And I always want to make sure I've pushed the record button because I do forget sometimes. Okay, the second kind is a geometric series, and there what you have your first number, which in this case is the same, 3 in both cases. And you might start out thinking, okay, there's 3 between here and here, and then there's 6, and you say, oh, obviously it's not an arithmetic sequence. You always assume they're arithmetic sequences until you're proven otherwise. So in this case, the number is getting larger. And so again, you would notice in this case 2 is the common ratio. Each subsequent number in the sequence is 2 times the previous one. So 6, 12, 24, 48, 96. And the next one would be 192. So I'm predicting it, and I would call it a geometric sequence. One of the things about geometric sequences is if you look at the difference between the two. So what I'm putting down here is the number in between, and so this difference, you can see the difference is doubling every time. And if you see something, the difference is going to have some kind of pattern as well. You don't need to do that. You can just look at it. You don't need to write that down. But I was telling my other class that just because it keeps my mind sharp, I like to do as many things in my head as possible in terms of math. I know a lot of people like to use calculators these days, but there was actually, I have a student in my calculus class, and his brother went to the Naval Academy, and he got a degree in engineering, and he got a master's degree in engineering, and he was talking about his brother said that he did learn to do math in his head because, you know, you're in a submarine and your calculator battery goes dead. What are you going to do? You have to be prepared. So imagine yourself in a submarine. You don't always have a calculator, but you always have your brain. So if I were to, the point here is, you know, how did I get 192? And we'll talk about this some other time in more detail. But there's these, again, Facebook has these things about Common Core, which is the standards. We don't use Common Core in Virginia. We use standards of learning, but they're basically a nationwide standard on competencies. And they also teach things in a different way, which the Math Common Core teaches you these, what appear to be very complicated ways to do what you would consider to be simple things. And so I was curious about that because I thought, okay, I don't have any children. Maybe my grandchildren would come to me and say, hey, Granddad, can you show me how to do addition? And I'd show them the old way, and they go, no, that's wrong. What do you? They say this is at school, and then so now I'll be able to answer their question. And when I've looked at it, not as a mathematician, but as an engineer from an engineering perspective, I actually think it's not such a bad idea because when you do things in your head, if you're good at doing things in your head, you do it differently than you might do it on paper. So here's an example. So if you were adding 96 plus 96 on a piece of paper, you would add 6 and 6 in the ones column, and you would write down, you say, okay, that's 12. I'm going to write down the 2, and I'm going to carry the 1, and I've got 1 plus 9 is 10 plus 9 is 19. So then I have 192. What was that number? I forgot my first number. You know, that would be the way I would do it. Yeah, I'm making that up. It was 2. So it's 192. So then one of my students said that. That's exactly what I do. If you see me out here doing something like that, they're basically doing that in their head. Whereas in my case, what I would do, there's a couple of ways you could do it. You could add 90 to 90, which that's easy. 9 plus 9 is 18. So I get 180. And then I take 6 plus 6, which is 12, and I add 12 to 180. And I get 192. And that's not the way you would do it by hand. But from another way you might do it is I'm going to add 196, and there's 4 different between this and 100, so I'm going to subtract 4. So it's going to be 196 minus 4, which is 192. So again, that may seem kind of crazy, but it actually is not so crazy. Or I'm crazy. I don't know which one it is. But. Okay. So here's another one. So why don't you write those numbers down and write down in your notes what you think the next term will be for both of these. So this is 2, 6, 10, 14, 18, 22, 26. And then the other one. Now we already know what kind of sequence. It's an arithmetic sequence because I told you what it was. Okay, and likewise here, you'll notice that if you start taking differences, you'll get 2, 4, 8, 16. But so you can see that it's not an arithmetic sequence. And so it's just a factor of 2. Each number is multiplied by 2, so the common ratio is 2. And so this is going to be 256. Okay. So you'll get some homework problems. I'm not going to do that. So this is on Facebook last year. You think all I do is watch Facebook? I don't. It just turns out that I saw this, and so the question is, can you see the pattern? It's not an arithmetic sequence or a geometric sequence, and I've forgotten what it is now. I know what the last 2 digits are. What's the first digit? Oh, I see it. Now, do you see it? I saw it. So what's the rule? Anybody see it? Yes, I think I know what so if you add these two numbers, you get this digit. So this plus that is 10, this plus that is 11, 13, 7, 13, 17, 16, 18. The number on the other side is, what was it? I just said it was. Oh, you subtract it. So 6 minus 4 is 2, 9 minus 2 is 7, 8 minus 5 is 3, and it works. Except, yeah, this one even works because this is added together as 13, 7 minus 6 is 1. How many people got that? Anybody got that? Okay, a few. So, I mean, there's not much you can do. You can multiply the numbers together, you can add them together, you can divide them. And so the first thing you do is add them together. That's what I would do because that's what it's saying. And that's when I saw this, and I thought, oh, okay, I got the last two. And then I thought, was it the number of numbers? But they're all two. There's two numbers in every. I was thinking maybe the number of parts in the expression. And because this was 2, and I thought, oh, there are 2 numbers. But then I got to hear it, and I'm like, oh, there's not 7 numbers, so that's obviously wrong. So then I thought, okay, what else could it be? So I said, oh, subtract. I added, let's subtract. So that was kind of how I came up with that. I'd forgotten, I had no idea because it was a year ago that I did that. Who knows what we did last year? Oh, okay. So I'm gonna click on. We're not gonna watch the video, but I'm going to just tell you about the video. It's a thing about learning. So I do every once in a while. I do these things as well. So it was actually written by the guy who runs the Khan Academy. Does anybody watch the Khan Academy? Yeah. Good. Nobody else uses the Khan Academy. Yes. Okay. What did you use it for? Math? Did you use it for? Oh, which subject did you do? Was it science? Which science was that? Was it biology or yeah? Did you take dual enrollment biology or just regular? Yeah. Anyway, in synopsis, it talks. So you haven't had any children yet, so remember this when you have children. So this guy is the Khan Academy. He was a business major in college, and then he made a lot of money on Wall Street, and then he decided to actually he had some nieces that needed help on some homework, and so he did these videos for his nieces. He sent them off to the nieces, and they apparently shared it with all their friends who were taking the class, and then somebody shared it with somebody else, and all of a sudden he's like, hey, apparently there's a need here for videos about math and science and other stuff. And so it's a good resource if you want to know about a subject. I usually watch it because I want to see how somebody else presents something. If I'm teaching something I haven't used it for a couple of years now because I feel more comfortable with things, but that's how I used it originally. And so, when your child does well on some assignment, a lot of parents would say, oh, you're so smart, you're so good at that. That was and so there's this whole concept of praising children too much, because when they get to something they struggle with, then they're like, oh, I'm not good at this, and I just don't want to try. So they give up. And so what he's saying, he always says, I like the way you tried on that. I like talk some more about the effort in doing it rather than how good he is. And so he's gotten positive reinforcement for the effort, because that's basically what you need to succeed in anything is the amount of effort. So it's an interesting article. If you ever, I may email it to you and you can just look at it. So here's your first assignment that you're going to include a short comment in the bulletin board of this particular class. So we were just talking about the Khan Academy. So I want you to go to Google Khan Academy, and then go and look. You should see a tab that says subjects, and find a math subject and drill down far enough so that you can
find a video, and then just record the name of the video that you're watching in terms of the title. And then you can also copy the web address for that particular video and include that in your response. So everybody should have a different response. If you copy somebody else's, then obviously you have not done your own work. This should take about 5 minutes, but it's so that you can go ahead and see the Khan Academy and verify that you are watching this video.
Here's another special kind of it's a sequence. I don't have commas separating them, but it's just another way. You look at that, and it's obviously not an arithmetic sequence. And even if you look at the, 3 times something is 14, but that's not going to be easy. That wouldn't be it would be 14 thirds, 14 over 3. So obviously it's not a nice simple geometric sequence. But it is one that ultimately does have a pattern to it. And you do have to do this on the test. So let me just demonstrate how it works. So basically you're going to keep manipulating this until you see something that looks like a pattern. So like you would do with an arithmetic sequence, you're going to subtract adjacent numbers. So I'm going to subtract 3 from 14, which is 11. And 31 minus 14 is 17. And 54 minus 31 is 23. And 83 minus 54 is 29. And 118 minus 83 is, let's see, 18 plus 10 is 28 plus, did I do that right? Yeah, I guess that's right. 118, yeah, that's 35. Yeah, 35. I don't know what I was doing. 18 plus 17, yeah. So again, I'm subtracting kind of a weird way. I'm taking 18 and I'm adding 17 because it's 18 greater than 100 and 17 less than 100. So you add those two together. 18 and 17 is 35. So I've changed the subtraction problem into an addition problem. Okay, now you look at that and you say, okay, am I starting to see a pattern? And I see it. You may not see it directly, but you do it again. So it's called the method of successive differences because you take the difference between 2 adjacent numbers and then you look at the next row and say, okay, do I see something? And you go until the actual number here is always the same, is the same. So then I do the same thing. So 17, so let me just write it out here. This is 14 minus 3. This is 31 minus 17, and etc. So I'm going to do the same thing, and I'll get 6, 6, 6, 6. So I finally come to something that this is an arithmetic sequence, and I know that because I've come down to this row, and all the differences are the same number. So then, to predict what the value is here, what we're trying to do is figure out what the next number is in that list. You go back the other direction. So what I'm going to do is actually write down a 6 here, add another 6. And notice if I go like in a triangle, 11 plus 6 is 17, 17 plus 6 is 23, 23 plus 6 is 29, etc. Likewise, if you go up one row, 3 plus 11 is 14, 14 plus 17 is 31, 31 plus 20. So it's kind of this V shape. So what I've done is I've added another item to this row where all the numbers are the same, and I just finish out the V. So 35 plus 6 is going to be 41, and then I do this subsequently. So let me write this is 35 plus 6 gives me this number. And likewise up here, let me just write it out. So so my final answer here is going to be 118, which is this number. Come down to the bottom of the V, write in 41. So I have 118 plus 41, which is going to be 159. Let me write that. That's hard to read. I did that right. Yep, 159. So again, it's just using inductive reasoning to predict the next number in the sequence. So I'm going to do one more, and you can do one for homework. This one's a little more complex. It's got another level, and I'm going to probably have to use my calculator. I'm not that good. So let me just plug the numbers in, and if you don't understand where I get the number from, just stop me and I'll explain it. So 19 minus 3, the difference here is 16. 165 minus 19 is 146. 771 minus 165. And I'll tell you on the test, I'll say use the method of successive differences to do this. So you 606. So 2503 minus 771 is 1732. $39. I think Jordan's keeping me straight here, so that's good, because I make mistakes. I don't tell my wife that, but I do. Okay, so obviously we're not finished yet. We've got quite a ways to go. So we did the next line, 146 minus 16, which I can do in my head. Okay, keep going here. Next one is 330. There is an answer, trust me. At least as you go down, you have less calculations to do, so that's nice. And I'm about to run out of space, so it's got to happen. It's got to happen soon. Oh, I took the wrong numbers here. So I think the next row is the one. Otherwise, we're in trouble. We're running out of space here. So we get 120. Ah, yay. Okay. So we finally do get down to the same number. So once you get down to the same number, then you can go back up the other direction. So you add this number, and then we just go back up. So I'm just going to, I need to be able to use the calculator with my left hand, so I don't have to keep doing this. So this plus that is that. Okay, so there you go. So, you know, we're going this plus that is that, this plus that is that, this plus that is that, that plus that is that, that plus that is that, if I did it all correctly. Okay, obviously you can't tell that from the original. You just have to plug and chug through the whole thing. Okay, you don't need to write this down. This is a little extra tidbit. So what we have is a sequence, which is a list of numbers. If you take those numbers and you add them up, so let's say it's 3, 6, 9, 12. So it's an arithmetic sequence. If you add 3 plus 6 plus 12, 3 plus 6 plus 9 plus 12 plus whatever. And the series is the sums. So the first one number would be 3, and the second number would be 3 plus 6, and the third number would be 3 plus 6 plus 9. And those are actually called series. And series are actually a lot more useful than sequences are. Sequences is just kind of an interesting number thing, but they're not really that useful. And so I'm going to tell you, you know, I've got one of these expensive calculators, and you've got things like, things you may, I mean, you know what sine and cosine is because you've taken geometry. Sine, and you may wonder, how the heck do they, when you put in the sine of 30 degrees and you get an answer, sine of 30, and I get a half. Okay, the sine of 30 degrees is a half. So how does the calculator actually do that? Because a calculator is just like a computer. It's a digital. It does digital stuff. It does ones and zeros. So ultimately, you have to break down somehow the calculation of a complex mathematical function into something that a simple binary operation can do. And it turns out that the equation, you can actually, if you take calculus, if you ever take calculus, you'd find this out, but it's interesting. So if you wanted to know what the sine of some angle is, and the angle would have to actually be in radians, which you don't know about, but it's just related to degrees by a constant. It turns out it's equal to x minus x cubed over 1 times 2 times 3 plus x to the 5th power over 1 times 2 times 3 times 4 times 5 minus x to the 7th power over 1 times 2 times 3 times 4 times 5 times 6 times 7. And so when the calculator actually figures out what the sine of an angle is, it's actually doing this calculation. And the more terms you add, you can see the pattern. So here's a pattern thing. You know, if I was predicting what the next term in this series is, and it's a series because I'm adding stuff together. Think about it. So you don't need to tell me, but well, somebody wants to tell me. So what do you think the next term would be in the sequence, in this series, just based on the pattern? So is it going to be plus or minus? Plus, because plus, minus, plus, minus. So the next one's got to be plus. Okay, so then we're going to have x raised to what power? Yeah, 9th power. And the denominator is going to be 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9. And then the next one will be negative x to the 11th power divided by 1 times 2 times 3 times 4 times 5. So again, we're using inductive reasoning to figure out what the next term in this series is. Instead of a sequence, it's a series. And it's amazing how few terms you need to get a good number for the use, you know, on your calculator if you're sine and cosine stuff. So if this wasn't available, I don't know how the calculator would actually do the calculation, because calculators can do algebraic stuff. They can multiply numbers together. They can subtract and add numbers, but they can't just, how do you know what the sign of something is? You really don't know. So. And actually what happens is you actually, theoretically, to get the exact answer, you'd have an infinite number of terms, which of course doesn't practically happen, but it's part of math if you have an infinite number of terms. Okay, and the last stuff is there's just a few formulas, just again to show you that there's a, I don't really know why they put this in this section because it's not really inductive reasoning. I think it's just some interesting formulas for making it so if you had, like we did with the, we did it with the Gauss the other day, right? We talked about Gauss and adding 1 to 100. So this is kind of the same thing. Here we're adding 1 to some number, odd number. And in that case, rather than being what we found out the other day, it was n. It would be n over 2 times n plus 1, I think, would be the equation. For an odd number, it's just n squared. So if this number here is, say, 5, so if n is 5, you get 2 times 5, which is 10, minus 1. So if you add the numbers between, let me just demonstrate how this works. So let's say n equals 5. So what you'll have is 1 plus 3 plus 5 plus 7 plus, in this case, n is 5, so you'd have 2 times 5 minus 1, which is 9. And that's, the formula says that's equal to 5 squared, because n is 5. So if we add all these numbers up together, 1 plus 3 plus 5 plus 7 plus 9, you get 1, 4, 9, 16, 25. So it works. So if I added the numbers up between 1 and 100, all the odd numbers between 1 and 100, it would be the same as taking 100, or 101, sorry. That would be when n is 50. So yeah, so or 51. So if n is 51, you'd get 101 here. 2 times 51 would be 102. Minus 1 is 101. So if you add all the odd numbers up between 1 and 101, you'll get 50 squared, 51 squared. So it's just a shortcut thing. And here's another one. If you add the numbers up, 1 to some value of n, and you square it, it's the same as cubing each number. That's kind of an interesting result. Let's just demonstrate that's true too. And we'll just go up to 3. So that's saying 1 plus 2 plus 3 quantity squared is the same as 1 cubed plus 2 cubed plus 3 cubed. So remember, you do parentheses. You do the operation inside parentheses first. So 1 plus 2 is 3, plus 3 is 6. So that's equal to 6 cubed, which I remember from the other day is 216. And so it's squared, sorry. I thought that was too big. 6 squared. So 6 squared is 36, 6 times 6. And here we have 1 plus 1 cubed is 1, 2 cubed is 8, 2 times 2 times 2. 3 cubed is 3 times 3 times 3, which is 27. And you add those up and you get 36. So that's an interesting result. Okay, I'll just give you, here's the homework for this section. What time do we have? 2:42. Actually, I've got a list of I said I was going to do, so we're going to do some in class here. I'm just going to let you write these down for right now. Once you get that written down, we'll do a few more examples from this section. Okay. I'm not going to do all of these. I'm just going to do a few just to show you what the homework's like. So let's try number 4. So number 4 is just a list of numbers. And what they're asking you to do is to say, is it arithmetic, is it geometric, or is it neither? So is it arithmetic? That means, is there a common difference between the numbers? And you should be able to see that very quickly because, you know, you've got 10 and then you've got some really big, you know, it's up to 60. So obviously it's not arithmetic. Oh, there's Travis. So it's not an arithmetic sequence. So then you try geometric. So think about geometric is really all you have to do is look at the first 2 numbers and find what the ratio is. So what's the ratio? The second number divided by the first number? 6. So then you try that in the next number. So then you say, is 72 12 times 6? And you say, yep, that's true. And then you try it again. Is 72 times 6 432? And you plug in your calculator, and it is. And so you know that the common ratio is 6, and therefore, so we say it's a geometric series. Once you've figured out there's some kind of common ratio, so we just say it's geometric. You just write that down. And then you pick the next number. So the next term is going to be 2592 times 6. So you get your calculator out, and you plug that in. 2592 times 6 is 15,552. And so that's the answer. Okay. You know, neither will be, if neither is if it's not arithmetic, which is easy because it's just a common number difference, or you take the first 2 numbers and you find the ratio and then you apply it to the next term, and if it doesn't match, then it's neither. So that's pretty easy. Then you do some of these successive difference problems, and I've already done 2 of them, so I'm not going to do any more. So that's, and then the final bunch of problems that you have to do is kind of like we did at the end of the last section. It says, determine the next equation, or the next number in the sequence. So let me just pick one of these. It's not too long. So this is number 24, and I'll write it down. So we have 1 times 8 plus 1 is equal to 9. 1, 2, which is 12. 12 times 8 plus 2 is 98. And the third one they give you is 123 times 8 plus 3 is equal to 987. So you just look, so then they ask you to write the next one in the sequence. So we're looking for a pattern. You see we have an 8 in every term, so that's not going to change. We see this one increases by 1, so we know the next one's going to be 4. We notice here we go 1, 1, 2, 1, 2, 3, so the next one's going to be 1, 2, 3, 4. And then the answer, you see the pattern, you just add the next digit is going to be 1 less than the previous digit. And so you would write out the answer would be 1, 2, 3, 4, 1,234 times 8 plus 4 is equal to 9,876. Okay, so that's pretty much it. Anybody got any questions or anything about this stuff so far? Okay, the next section in the book, it's called the Strategies for Problem Solving. And the problem with this section is if you go back and it says here, I'll read it to you. One of the popular features in the journal Mathematics Teacher, published by the National Councils of Teacher Mathematics, is a monthly calendar, and it provides interesting problems. Well, these are problems that are for math teachers. Why are they putting it in this book? I have no idea. They're not easy. I've scratched my head on a few of them. So I'm going to sign a few problems out of here. If you can figure it out, that's great. If you can't, don't worry about it. Just watch the videos and answer the questions based on the videos. I just want you to get a few examples of the thought process that goes along with solving these problems. Teaching you how to solve problems, we're going to have to do that throughout this semester. It's not going to be something that I can do in one section of one book. It's just not going to work. So what I'm going to do is I'm going to just go through some of their discussions, but don't write them down. They're in your book. So let's just try to pay attention as much as you can, and I'll add my own little bits from 57 years of problems. Well, I've been doing it since I was born, but you know, since college. My physics students have a hard time solving problems. That's part of the problem with SOLs. They don't teach you how to solve problems, and I can't solve it overnight. Okay. The last section, before we get to it, just to let you know, it's called Calculating, Estimating, and Reading Graphs. So it's about graphs. So we looked at some graphs today. What I'm going to show you how to do, and then you're going to do it as an assignment, is you're going to use Google Sheets. Has anybody ever used Google Sheets, which is the Google Docs form of Excel? How many people have used Excel before? Just a few people. Okay, so you're going to learn how to use Excel, well, the Google Docs version of Excel. And you're thinking, this is a math class. What is he doing to me? I'm not going to be able to learn spreadsheet in, well, it turns out that one of the videos recordings you have basically shows you how to do it. So you're going to go through it, and I'm going to show you step by step as a recording. You'll do it at home. So you'll at least get some experience with it. You'll at least say, I've done it. I kind of at least have some idea of what I'm doing. And it'll allow us also to talk about different kinds of graphs. So that's how I handle that. We're also going to look at a whole bunch of different kinds of graphs. I found a whole bunch the other day, so we'll just see how we can do something. I'm trying something new. Okay. So again, don't write any notes. I'll just okay, so there's this guy, Polya's four-step method for problem solving. The problem people have with solving problems is they try to do too much at one time. You know, they read the problem and they just don't absorb it. But you have to remember that the math problem is not a novel. It's not something you can just kind of skim through and say, oh yeah, I get it. So as it says here, it says you cannot solve a problem if you do not understand what you're asked to find. The problem must be read and analyzed carefully. You may need to read it several times. After you have done so, ask yourself, what must I find? So don't just read it one time. You got to read it multiple times. You kind of read it over once just to kind of get a general sense of what the problem's about. And then you typically, like in physics problems, you know, you're given some information and you have to calculate. So you're given something and then you have to decide what they want. And then in between, you got to figure out what formula do you use, technique do you use to solve the problem. These problems that are in this end of this chapter don't fall into that well. It takes a lot of, it's not, you know, there's no formula. Okay, so read it slowly. Math texts are not English texts. Devise a plan. There are many ways to attack a problem. Decide what plan is appropriate for a particular problem you are solving. So obviously, in math textbooks, you know, they're not going to put a math problem that has to do with sections that were 10. It's to do with what's in the book. You know, whatever section you're reading, the problems should be related to that. So if I'm reviewing something, I'm teaching a new class that I haven't had the material for 20 years. How do I learn the material? And what I do is I read the material, and then I go to the end of the chapter and I work the problems. I look at the problems, and then once I understand what they're talking about, because a lot of times you read math textbooks and you're like, what are they saying? I don't understand what they're saying. So you actually work a problem, and then you go back and you read it again to try to understand what they said. And so you don't want to spend all this time reading the stuff until you finally understand it. You read it some, and then you go work a problem. And also, if you look at the textbook, how much of the textbook is example problems? It's probably 75% example problems and about 25% telling you how to do it. So I always look for an example problem. So if you don't go back and use your book and look at example problems, then you're destined to mess up. And typically, each different kind of problem, there is an example somewhere in there. The textbooks today give you much more examples than you used to. When I took calculus in 1975 at college, freshman year college, I still have my books, which Martha thinks is crazy. Why do I still have a book? My wife's, I don't have any of my old books. But anyway, I have my old books. And I look back at that and I go, oh, that was a terrible textbook. And part of the reason was because they didn't have a lot of examples. But even then, that's what I had to do. You had to go back and say, they're not going to be as sadistic as you think they are. They're going to show you a problem that's maybe slightly harder. So you just have to mind the examples. Okay. I'm watching this thing. I don't know if I told you the other day. I'm watching this TV program on public television about the scientists who discovered, the chemists who discovered all the properties of matter, and you think that people just make these brilliant discoveries out of nothing, and the reality is that each discovery is dependent upon somebody else making a small previous discovery. Very rarely do you get Einsteins that make some kind of, or Stephen Hawking or somebody like that, who makes something that's a huge leap. And the same thing with solving problems. If you read a problem in the back of the text in the problem section and you don't have any idea what to do, you have to remember that they're providing you with examples that are hopefully leading you almost to the answer, but not quite there. So you just have to go a little bit further. Okay. Okay, so then you come up with a plan, then you carry out the plan. Not all your plan may not be right. That's sometimes you might work it and find out you run into dead ends, so you have to be a little persistent. That's the danger of me recording the solutions, because you might look at the problem once and say, I don't know how to do it. I'm going to go watch the recording. You don't want to spend hours going into multiple dead ends. That's a waste of time. But it's not, getting stuck is not a problem. It's actually good for you. In the real world, the answer is not multiple choices. So you may go through iterations, and it's a good experience. And then once you get an answer, besides looking in the back of the book, you might be able to go back and check to see whether the answer makes sense, or whether you can plug it back in and see whether it's verified. A lot of people don't do that. What I do a lot of times, say in my calculus class, I'll make up a problem. So I don't know what the answer is, because there's no answer key for me making up the problem. So I'll work through the problem, but I want to make sure that it's a solvable problem, and that that I know what the right answer is. So if somebody comes up during the test and says, "Can you help me out?" and or give me a little hint. So what I'll do a lot of times is I will graph the solution. I use graphing. So if you come up with a solution, there's other ways of checking it. You can't always just plug it back in like you can with algebra. You solve algebra equations, like you have two equations and two unknowns, you can always go back and plug it in and make sure it works right. Or if you have just one equation and one unknown, you can always solve for it and then check it out and make sure it works. That's the easiest way. But a lot of times I assume that I did it wrong, and I check it out. So there are a lot of cases where you can do that, especially in tests, to make sure that you don't make a mistake. So don't, and I tend to make the tests short enough that you should have time to go back and check things out if you understand things. If you don't understand things, you'll never do it. Okay, so that's the process. And here's some hints. We kind of probably alluded to some of these. You make a table or a chart. Physics problems, you always want to draw pictures to understand things. Just looking at numbers and words, it's not always it's the best thing to do. You look for a pattern. We've been doing that. Or looking for a pattern, maybe looking back at an exercise that you've already done and say, oh yeah, that kind of looks like what I'm supposed to do now. Maybe I can work it out. Solve a simpler problem, okay? Typically, in this book, not so much, but in more advanced math textbooks, the first couple of problems will be easier and then they'll slowly get harder. So you wouldn't assign just the hard problems. You'd assign the easy problems so you become more confident about things. Draw a sketch is kind of like making a table or a chart. Use inductive reasoning, which is, we've been using that. Sometimes you just have to try an equation and see if it works or not. If a formula applies, use it. Work backwards, that's a hard one to do. So I'm not going to talk about it. Sometimes trial and error, use common sense. And sometimes if a problem seems too difficult, it may be because you're solving it wrong. Again, in calculus, you can really go crazy and go in the wrong direction. And I usually tell students that if you've got something that looks too difficult to solve on a test, obviously you've done something wrong, because I'm not going to give you something that takes that much time. So if you think, if things look like, especially in a test situation, if you think things are much more complicated than you've seen before, it's probably because you're working the problem wrong. There you go. So there's your homework. So like I said, you just think about them. Give it a good try, but don't spend a huge amount of time. And you'll hear me talking about some of the thought processes, but it's we'd have to spend weeks on this to actually get good at it. We don't have time to do that, so we will work on it during the semester. Okay, let me just, oh, there's Travis, so make sure he's taking account of here. And let's see, you were late and I've forgotten your name. You're Hannah Markham. There you are, Hannah Markham, okay. Then nobody else came. Oh yeah, you did, somebody, so let's see. Let's see if I can figure out who you are. You're not Margaret. So you're probably Kelly. What's that? Right here? Yeah, so you're Kelly. Because everybody else, I think, dropped whose name's on here, who hasn't attended yet. Okay. Do we need to turn in the in-class homework as well? No. That was just to remind me of the problems that I'm not assigning for homework. Okay, so we're going to move on to section 4. So again, we're going to look at a series of different kinds of graphs, and I'm going to point out the important things about graphs, what you look at, how you look. Maybe I'll ask you some questions about the graphs. The calculating, I don't know how you calculate a graph. You plot a graph, you don't calculate a graph. We'll do that using, so Monday or Tuesday, we'll just, if you want to bring a laptop and kind of go along with me on it, that would be nice, but you don't need to, because it'll be recorded. Okay. So here's a word of warning. Don't trust anybody. No, I shouldn't say that, but it's like that soda thing with the sugar. I looked at that and I thought, that doesn't make any sense. You always have to question things, especially nowadays. I don't know whether, it just seems to me that especially commercials, political commercials, you can't trust. They never tell the truth. It's always no matter whether it's Republicans or Democrats, it's always some way of tugging at your emotions and trying to get your emotions to override your common sense or your logic. If you watch TV recently, there's that, and I have sympathy for the guy, but and I'm personally, I guess I can't really say for sure. I'm not a nuclear scientist, but there's the one where there's the guy that's been injured by the bomb in Iraq, and he says it's an Iranian bomb, which it probably was, made in Iran, and that really is emotional. You see, how many people have seen that commercial? Because it's been on so many times. You see that, and every time I see it, I feel bad for the guy. But the alternative, you have to think about, and I'm not sure which way I go on this thing because I don't know enough about it, but the alternative of there's more money going to terrorism. Yeah, that may be true, but do you want the only option? Well, the other thing is that if we don't lift sanctions, the Europeans are lifting sanctions anyway, so they're getting money. And then there's no way to verify that they have any nuclear stuff, so you're basically shooting yourself in the foot. They're going to get their money from someplace else, and they're going to not have any verification, so that's not good. So if you don't verify, if they don't sign the treaty, then you're basically saying, no, our only response is war, and we don't need any more war. So that's just one example. It's not a graph. It's just how people use emotions to. So you got to be careful all the time. So anyway, and even in graphs, this is supposedly data, but graphs can be misleading as well. So you got to be. Okay, so let's just talk about these different kinds of graphs. Let me zoom out a little bit. So if anybody wants to talk about current events, I'm a current event person. Okay, so this is called a pie chart. I think there's another name. U.S. immigrants by region of birth. And so you have the numbers for most of the cases except the other. They don't tell you what that is, but you could figure it out because that the total has to add up to 100%. So we could figure out what that is. We have a title. We have labels, which are showing us which each part of the pie is worth. And we're using different colors as well. So a lot of times pie charts are different colors as well. So they're good. They're good things. You got your source of your data as well. Okay. Let's look at another one. These are out of the book. I've got most of the other ones I've got out. They're not out of the book. So this is one of these vertical bar charts. And so you could have a table with the same information, but it's much easier to look at relative amounts when you're doing it graphically. Notice that, oops, I'm getting hungry. Notice this graph is a little misleading because they have 0, then they go to 160 to 165, 170. Actually, I don't like that. I wonder if that was why that's in there, if they're just doing that to mislead you. So, you know, you could say, if you looked at that without actually paying attention to the scale, you would say, oh, the milk production is almost 3 times what it was in 2001 versus 2007. But if you actually included between 0 and 100, you would have a better, more realistic representation of the differences between one and the other. If you're using the height of the graph as a basis. But the advantage of this kind of graph is that you get to see the difference. You're able to see the differences more so. If you wanted to look at the numbers, if you went from 195 down to 0 with all the ones in between, these differences would be much smaller. So you have to be careful about how you do it. There's advantages to doing like it is there. It accentuates the changes, but it sometimes misrepresents how much absolute change you have, the absolute values. So again, we have our title. We have a title, our labels, our title, and in terms of these are called axes titles. Horizontal axis, vertical axis. That's our label. Oh yeah, okay. Let me share that with. Here's some graphs. I was thinking it might be interesting to look at things during the semester about employment and careers in a graphical format, so I'm going to do that. College majors least likely to lead to underemployment. So what that means is, you know, you get a degree in English and you work at Starbucks or something like that. You don't use what you've learned. So here they are. These are horizontal bar charts. I don't know what are the units on this thing. Actually, they don't really say what the units are, so you have to be a little careful here. Well, I guess it's percentage of majors who are doing or have jobs that are less than what they were trained for. So if you're criminal justice and you're selling furniture or something like that. So let's just look at them. I was kind of surprised that criminal justice, business management and administration. So that's an interesting thing because, you know, a lot of people go into college and they get a business degree because they think that's going to make them so they can work for somebody. You know, businesses are people who employ workers. But actually, the number of positions that actually will hire people out of college, if you're an accountant or if you're a finance major, more so. If you're business management, that's not as employable. General studies, sociology, psychology. Here's a fun fact. I already kind of gave you the answer. My daughter, Heather, went to occupational therapy school at VCU. And it's very competitive to get in. I mean, this year, I know somebody who got accepted this year, and I think they had 400 people apply, and there were 40 people that were admitted, so it's pretty competitive. And when Heather was working on her undergraduate, she got a degree in psychology, which, as you see, is one of the more unemployable or underemployed majors. And but she did it with the intent that she was going to occupational therapy school. And at the time, I thought that was okay. I understand that a little bit. I would have thought somebody maybe was majoring in healthcare, some kind of healthcare or biology, would be more likely to be the major that they would be looking for. And it turned out she got still gets to send to our house, and they had a newsletter showing the class, the current class, and and their majors, what majors they had as undergrads to get into graduate school. And it turned out that it was the major that was most accepted was psychology. There were 14 out of 40 had psychology degrees, so I guess it wasn't as crazy as I thought it was at the time. But so now, if she didn't get a job, if she didn't get an occupational therapy school, then she would be more likely underemployed. But so anyway, and then you have over here the least underemployed majors. So what you see is engineering, physics, mechanical engineering, geology, all the STEM stuff. Lawyers, that's probably getting a little bit longer. There's an oversupply of lawyers right now. Because the lawyers, it used to be, does anybody have any relations that are lawyers? Any family that's lawyers? Okay. So yeah, anyway, there are too many lawyers right now. I've read articles about that. A lot of times people get an undergraduate degree in something like history or political science or liberal arts, and they're underemployed. So how do they get a good job? Well, the traditional way of doing it was to go to law school. And so there were a lot of people that wanted to go to law school. And anyway, there's an oversupply right now. Okay, so what we'll do is we'll just continue on looking at some examples of different graphs and talk about them and how they're either good or bad at displaying information.